All right, cool. Thanks everybody for coming to this session, and I know we're the last talk before lunch, but we have a lot of material, so get comfortable. Andy and Patrick and all the AV staff, thank you for hosting this amazing event and having our company pay for us to come to Maui. So just a quick show of hands, who in the room does macOS malware analysis? How many of you kind of write signatures based off of that work? And how many of you use YARA? Cool. And last question, do any of you write malware for the Mach-O format? All right, hell yeah. I know that you guys are going to get some devious ideas out of this talk, but I'm Greg Lesnewich, and this is Jacob Latonis, and we're from a company called Proofpoint, and Jacob, you can take it from there. Cool.
Can everyone hear me? All good? Okay. So the agenda today, we're going to start with, we're going to go over some DPRK malware, some crypto stuff, how we effectively track that. We're going to also go into the similarity methods that we developed from trying to track these pieces of malware. It's going to kind of ping pong back and forth from Greg and I. We're going to talk about the malware. We saw the artifacts that we decided to pivot and analyze, and then we're actually going to go into how we parse them from the Mach-O format. And then we're also going to show other wins that we developed from parsing those and pivoting on them.
Cool. So why look at similarity measures, and particularly in the way that we are with just parsing the Mach-O itself? The state of current analysis when you get an unknown sample is relatively repeatable. You pull out binary metadata information, whether it's the cert, the dilibs, the imports, and then as things progress and you are either dumping strings or the symbol table or going into a disassembler, those things aren't necessarily, especially for a lot of you in the room, harder, but they are more time intensive. And so our idea was, can we apply something to find sort of similarity on the metadata level rather than just on the code blocks or on the strings. And part of that is because I've come out of analyzing Windows malware for so long, and we have so many, go into VirusTotal and you click a button and you can get an idea of the global prevalence of something really, really fast. Whether that's the import hash, a hashing of the rich header, which has a bunch of compilation environment information, or more like user understandable artifacts like the PDB path or the DLL name. And so we wanted to sort of explore what we could do sort of as a similar to these things for the Mach-O format.
And you may be wondering, where did we decide to actually implement these things? You probably know from the title, ended up in YARA-X. We bounce back and forth between writing our own tool to parse these things out or to actually implement it somewhere else already in the ecosystem. And YARA-X just kind of made sense. I'm a big Rust nerd, so it fit in right away. If you're not familiar with YARA-X, it's a YARA rewrite in Rust, so there's safer parsing. There's a big performance improvement. It scans pretty quickly. Tomas over, I think he's at Avast still. He and I worked on the Mach-O module quite a bit. And if you were familiar with the Mach-O module with original YARA, it was never actually fully baked into it. You had to build it from source by yourself, and it got a little messy because there was some unsafe stuff in there. Not anymore. It's perfectly safe. You can parse things, have fun, and write rules for it. And it also provides a lower barrier of entry for tracking an actor and family, right? Like you can just point and click, get some form of artifact or write a rule and get up and running very quickly.
And what sort of started this was my primary job at Proofpoint is North Korea. And so if you just search the term North Korea on Patrick's site, you get most of the blogs that are on Objective-C's website. And that is just where the threat is going, and it's most prevalent. So we wanted some easy buttons implemented in that way. So for those of you that are unfamiliar with why are we talking about a country and at a security conference showing you a map, I actually think the context here is really important because North Korea is a really isolated country that is adversarial, I think, to everybody's host country here. And they have a really long history of stealing money through a ton of various ways, whether counterfeit cigarettes or illicit cigarettes, counterfeit US bills. If you remember the Bangladesh bank heist, their current flavor of that is just cryptocurrency. And the current estimate that we all kind of agree on is that in the last 6 years, they've stolen roughly $3 billion in cryptocurrency. All of that money goes to the WMD and missile programs. That is not oh, cool, we're a cyber criminal group and we're just kind of making money. That is that money is getting used for bad things. And I actually wanted to thank all of you in this room because every time you do something to write a detection or improve the safety of the macOS ecosystem, you're preventing bad people from getting nukes. So I wanted to thank you all for that. And now that I've buttered you up, I want to talk about the groups and give us a little bit of a reality check because we shouldn't say that L word anymore. Part of that is mostly an Intel problem, and we've done a really bad job of explaining to the malware space and the security research space that North Korea actually has a lot of different groups, very distinct ones operating in the macOS and cryptocurrency ecosystem. And so I take part to blame for that, but don't worry, we're gonna have a guide for how you can attribute each piece of malware that you're looking at relatively easily based only a little bit on vibes, but mostly on data. So let's get into the actual groups that we're gonna sort of talk about today. We can just call these the DPRK attribution ABTs. Apple Juice, that should say Blunar off on the top, and Trader. Effectively, they're all very different, both in the malware they use, the infrastructure they deploy, and frankly, the people that they target. We're going to get a little bit deeper into each one sort of as we explore a couple of their main backdoors that sort of drove the need for this similarity set of measures. So we're going to start with Apple Juice. And Apple Juice is sort of like the utility player among a lot of these groups. Supply chain attacks, they got them. Browser O-days, got those too. Trojanized Python projects as well. And they have dedicated Windows, Mac, and Linux malware. And they tend to go after, like, directly after crypto entities. And their supply chain attacks are sort of crimes of opportunity rather than really dedicated, like, this is the only way in. And so if you saw the blog from Viper, I believe, with PyPy packages that were Trojanized that would download a family called Pondrat. They also recently, Microsoft blogged about them having a Chromium O-day so they could escape that browser sandbox and then kickflip directly into the Windows kernel with another Windows O-day to deploy a rootkit, which is just like you're skipping stages 2 through 6 and going from Chrome O-day to rootkit, which was sort of insane. It also does a bunch of unhooking, which is pretty crazy. If you go look up the FUD module rootkit, you'll find some really interesting work out there. And ironically, which is what's gonna, I promise, get us into the actual Mach-O malware here in a second, is they actually used a different Chrome O-day to compromise an entity called Trading Technologies. That access was then used to get into the 3CX build environment, which is where our similarity story really starts. And if you remember the 3CX incident, and as it played out and all the subsequent analysis was done, it was pretty obvious on the Windows side of things that it was super similar to previous Apple Juice style intrusions, from a shared RC4 key that was unique to the group, the kind of uniqueness of the SRDI shellcode stub, and the magic bytes that were used were all very Apple Juice-y. But if you remember the update agent payload that Patrick blogged about, it was not that impressive, and sort of frustratingly, when we would go back and look, because there were only like 6 unique functions that you would really have to write SIGs on, and a bunch of very unique strings, we were having no luck finding similar stuff. There was basically only this update agent thing, and it was obviously a dedicated code base. And so our thought was, what if we go back to this binary metadata concept and see if we can find similar stuff?
So as Greg mentioned a little earlier, we took a little bit of inspiration from things like imp-hash with Windows. There was an initial sim hash written by the guys over at Anomaly back in like 2016, 2015, and it only hashed the symbol table. So we wanted to build on top of that and see where we could improve and do a lot of cool things. So the first one that we started with is dilibs. If you're not familiar with dilibs, it's just dynamic libraries for doing things at runtime. They're often bundled with the binary itself. And if you've ever written a YARA rule to actually look for dilibs in a Mach-O binary, like before right now, you probably had the strings hard-coded. You looked for the dilib load command, which is important. We're going to talk about that one next slide. But so you first check if it's a Mach-O file. You have to then guess the offsets for where the load commands are in the binary, and then you have to just kind of hope they're there. So if the strings are there, but maybe they're part of something else, you can get false positives, things like that. Guessing the offsets isn't that nice. So with YARA-X and the Mach-O module, what we implemented was If you're familiar with the Mach-O structure, it's basically the header and then a bunch of load commands kind of saying this is how it runs, this is how things are going to work. So we parse out all of the load commands that involve dilibs. You can see in the bottom left, it's a little difficult to read, but there's more than just that lc_dilib. There's id dilib, there's loading the weak ones, there's re-exports. So we're gaining a lot more context here on the dilibs used in the binary. And then if you were curious, this is how you parse it with nom and rust. So we actually get a lot more information than just the dilib name. So we actually get the offset into the binary, the timestamp of which it was compiled. Sometimes that gets stamped out. You'll notice if you look at dilibs inside of like things that were written by Apple, the timestamp is always 2. That's not documented why. If you've ever looked at Apple documentation, it's ass. So, but you also get a current version, which we break out into a string, and then we also get a compatibility version as well. And then we parse the actual C string of the dilib name. And then we wanted to figure out how to actually make that useful for everyone, because if you have, a list of 90 dilibs, writing that into a rule is pretty slow, ineffective. So we came up with dilib hashing, building off of like simhash and things. So what we do is we take all of the dilibs that were present in the binary that we parsed. We go ahead and grab all of them. We make sure that they're trimmed, so no white space. We make sure that they're lowercase. And then we dedupe them, we sort them, and then we join them with a comma. So this is very similar to how imphash and simhash do it as well, so we're keeping it consistent. And this is guaranteed to be deterministic, right? So if you have 2 different binaries that have them in different orders, it'll still produce the same hash.
And so in our initial experimentation, this is effectively why this took off for us. If we worked backwards with dilib hashing all of the local samples that we had, which admittedly was not as much as like Jaren's presentation yesterday, this was only catching old apple juice samples, which was really exciting for us. It was much more of a tell that the developer behind these different families had a very distinct set of build preferences and requirements. And so it was cool to go from, okay, we're not just tracking the code base, we're tracking the developer and their preferences. Albeit, if we saw the previous slide that we were sort of looking up all those dilibs in YARA in VirusTotal, we had 10,000 hits and it was false positive city. When we started running this locally, we only have 47 files. So even if that is not just the singular way of tracking that stuff, being able to use that as a selector and parse down the data set you're working at, 47 files is a lot more manageable set of Mach-O binaries to look at than 10,000 or 1,000.
And you might wonder if we want to get a little bit more granular. So say 2 pieces of malware use the same dilib hash, but you need to track them in a different way. You'll notice on this, we have over 20,000 files. We matched on 17 of them, but you'll notice that there's both APT 37 and APT 28 and some other stuff in there. So if you need to get a little bit more granular, that actually goes back to those being able to be precise via those versioning artifacts that we parsed earlier. So what we can actually do is we can specify the hash, and then we can check if any of these have a specific version, and then kind of anchor down from there. So you can see that we get a little bit more granular, and we can track a bit better. And these are parsed out as strings. They're ints in the actual dilib, but it's a lot easier for us to remember like 1.0.0 instead of whatever. Well, I mean, the int is just 1 for that one, but you get the point.
Cool. So the next family up is Blunaruff, aka TA444, aka Stardust Shalima, Sapphire Sleet, whatever you want to call them. I realize that the naming convention in Thread Intel is obnoxious, but it's not going to change. So I will keep them memorized, and you can just ask me what they are. I review my flashcards at night before I go to bed to make sure I can get them right in the morning. So this is more of the upstart. They make up for a lot of comparable technical sophistication with social engineering and persistence. They have some cool tooling. Like the candy corn backdoor that Elastic blogged about, and the Joker spy and their sort of TCC bypassing tool set. And they tend to target, instead of crypto entities now, crypto whales. So if you're a member of any sort of rich person that talks about, oh yeah, like I hold a lot of crypto, I hodl, you're probably going to get targeted. And so for initial access, they use a lot of both phishing-esque things, both direct download or a bunch of fake PDF readers, and Trojanized Python or Java packages. Most recently, we've seen them using this fake meeting lures, enticing crypto traders or tech leaders to join a fake Zoom session, allegedly from venture capitalists. You get all excited to join this meeting, and you click the link, and you get this. This is only available for macOS. In the background, you're actually getting a gross Apple script file that is running and then downloading an additional binary to run on your computer. And of course, you don't actually get the call from the VC to get funding. You just get malware. They've also used Java or Python files when sort of doing like the dream job style lures for targeting developers. You'll effectively get offered to run a bunch of test code for them and say, hey, what's wrong with it? You obviously don't find the backdoor in it. You just run it. And they'll use this to download stuff like spectral blur or the candy corn backdoor. And they're kind of like the riff masters of the space because they are just always coming out with some gross new loader as an intermediary between the social engineering aspect and the ultimate actual payload, whether that's candy corn, Rust bucket, or spectral blur. And they do love, because they're obviously keeping track of Amos, running a bunch of different tools to just run an Apple script to eventually download a next stage payload. It's sort of just a known thing in our space that if you're looking at a piece of macOS malware and it's kind of in a weird language, it's probably Bluneroff. And so Candy Corn was sort of the next family that we looked at for this sort of similarity idea. And one of the things that really stood out to us as we started analyzing it, and if you read Elastic's blogs, you'll find this too, is that it was super feature-rich, and there were a lot of strings left over, both as symbols and just sort of in the strings table. And I sort of got paranoid thinking like, well, what happens if they change that? What happens if they evolve the code base? Can we still track it? And of course, we're up here because the answer is yes. And so despite the updates to some stuff in the symbol table, as well as the protocol getting tinkered with per Salim from Elastic's Virus Bulletin talk a couple weeks ago, we're still able to track that both across the ARM and the Intel binary. So this ended up being a decently resilient measure of hopefully we can track this developer with this relatively weak signal because those are the only binaries that we're finding. And I don't know if this is going to be a perfect signal going forward to finding these guys, but if my process is find the binary, see if it's in VirusTotal, click a button once to get the global prevalence, that's such an easy measure and pivot for us to make that why would we not do it? And so one of the other things that stood out in the candy corn sample that led us to our next sort of artifacts that we wanted to look at were these odd entitlements, and particularly that Henry string, which obviously isn't returning true. So where do we take that?
You've already heard about entitlements a little bit in previous talks, so I'm not going to dive into that too much, but they're just rights or privileges that give applications specific capabilities, whether that's on Mac or iOS or what have you. And it's XML. We have unique characteristics that we can look into. Sometimes we'll see that some entitlements, they put it in there and then they do false. I don't know why they do that, but it's there sometimes. But most of the time when they are requesting something, you get the key and then you get true after that. And if you are curious about parsing them or looking into binaries and doing it on your own, believe it or not, they just chuck the XML in at offset like as a string, and then the parent application deals with it. To break it down on how you actually get to those offsets and how you can get into it, there's a CS superblob, which is kind of the first thing that you get from a load command. And then you have to parse the superblob into a bunch of CS blobs, which have a bunch of indexes. And then from there, you check, each blob has a magic byte sequence that tells you what kind of blob it is. And then from there, you can parse the embedded entitlements. It may be the certificate information. We're working on that one. That is not in YARA-X yet. I had to handwrite the ASN1 parser because Apple doesn't follow normal things with DER and BER formats. They do indefinite length, and every parser in Rust gets really mad. So I'm working on that one. That one's coming soon. But once we parse those out, we actually are able to generate an entitlement hash very similar to what we've done in the past. So we take the keys. We also take if they're true or not. So if they're true, we store that as well. And then we do the same thing. So we dedupe it. We order it in a concrete deterministic way. We lowercase it, make sure everything is all good. And then we generate a hash just like that. And because of that, we were actually able to do something pretty cool. Going back to Bluneroff, which we were talking about earlier, they have a first stage PDF reader, and we were actually able to get all of them clustered together with this rule that appears unique to that family. So everything else changed in the piece of malware, but we were able to cluster them with the entitlement hash alone. And because of the good fortune that we've had with being able to cluster and looking at these entitlements, we also get to do it in iOS since they share the same binary format. So we have a lot of wins. With this one, you'll actually see that we were able to track operation triangulation samples together, just solely based on the entitlement hash. We're not claiming that we could have discovered these earlier or that this could have improved analysis, but it is worth noting that these artifacts that they have left over that are not directly in the binary or directly something dropped by the binary, we can get the entitlements and use those to actually cluster. And we see a similar thing with LightSpy on iOS. We were able to similarly link those together as well.
Yeah, and going back to our original case with sort of the apple juice set of families, we started then hashing, and we got really good signal by combining the dilib hash and entitlement hash, which again is a very easy pivot. And what was cool is that when a new family got discovered and published about by Palo Alto, who I believe is a sponsor of this event, so thank you, Palo Alto, they call it Gleaming Pisces and a family called Pondrat. We were actually able to have forward detection of that and say, okay, without even looking at the binary or opening a disassembler, we say, okay, this matches known apple juice sort of like developer preferences. Do we even have to triage it versus just condemn it? So it was pretty gratifying to have that work out that way. And because Steelers are all the rage, we had to get in on that. And I sent this rule over to Alden yesterday, and just hashing on the dilibs and the entitlements without ever having to ruin my day by opening an Amos binary in Binary Ninja. That rule, with no real effort other than Jacob having to write all the parsers, caught 488 of Alden's 491 files. So I think that's a little bit over 98%, which is a lazy man's win. So we're going to get to now the most mature and hardest to track actor of the bunch. Trader, aka Jade Sleet. Internally, I get to call them Unk Macho Man. You'll understand why in a second. And this is sort of the A team among all these actors. They have really well planned out supply chain initiated intrusions, and they'll tend to do like sort of the bridge targeting that you hear about, where a bridge gets knocked over. It's not necessarily just like a wallet or funds getting stolen, but the bridge getting exploited and compromised. So that's these folks. And in my opinion, they have the most interesting set of Mac malware really in the space. And we assess these actors are part of the original crew that knocked off the Bangladesh bank and a bunch of those other original bank heists. So they're well versed in the macOS malware space. And they have a couple of mainstays in their arsenal. For initial access, as we sort of talked about, they were part of the jump cloud intrusion, or they were the jump cloud intrusion. And they were also part of the Circle CI incident from earlier in the year. And they have a couple of really cool families. They also have used spear phishing as initial access, both into jump cloud and then into targeting Russian defense entities previously. That was on the Windows side, but they just so happened to have a PDF exploit laying around for that spear. So they sort of scare us a little bit because we don't see much use of their O-Day because they're really good and they do a really good job of hiding themselves. So, but they do have a couple of mainstay families. The first of theirs is Beefeater, aka Full House, aka Two Pence, aka Voltaic Fish. I'm not making that name up. And over the years, it runs on both the Windows and Mac side, but it evolved from effectively a tunneler into a fully fledged backdoor. And it was prevalent for a really long time because of the byte sequence you see, those magic bytes there. All the symbols are still intact in a bunch of the original binaries, so finding the magic packet that it would send outbound for its comms was really easy. So we would track both the samples and then spray those magic bytes around the internet to try and find their C2s. And around 2022, the protocol started changing, and then a bunch of the C2s sort of fell off the map, and it disappeared from our visibility. But then the Mandiant Jump Cloud blog happened, and we had a sighting of them again. And the Full House, what Mandiant called fullhouse.dord, it sort of stood out to us because they wrote a YARA rule for it that was super regexy, that made it a little bit tough to read. But what stood out was this Mac dash and SHA-1 part of the self-sign code signing. I still have no idea what that value after the Mac string is, so if somebody afterwards wants to explain that to me, I would be eternally grateful. But what was a real win was after getting a sample got pushed onto VirusTotal, the original Beefeater sample, I think that Patrick has probably analyzed and is up on the blog, had the same dilib and entitlement hashing as the one from 2024, which is pretty cool to see that, again, these developer preferences do stick around. But we, of course, this wasn't enough. We wanted to keep exploring and see what else we could do through the binary metadata.
So we decided to then go towards imports and exports. Basically, if you aren't familiar with Mach-O exports, we're going to throw it back to like your CS 200 data structures course. They're stored in a Mach-O binary as a prefix tree. So it goes from longest prefix, and then it breaks down each node into the next character. So if you want to parse these out manually and look at them and kind of get into it, I have a couple of algorithms textbooks from college, if you're not familiar, on how to like depth first search a prefix tree. More than happy to talk about it. But I hadn't encountered them since undergrad, so I felt it really important to mention that Alden hadn't either. And then with imports, this really is like a flex in the Mach-O binary that like they just wanted to do cool things on how to store the strings. Because imports are stored within the binary and rebuilt via finite state automata. So basically, you have a like little CPU that has opcodes. And then you have to parse those opcodes, do the instructions indicated by those opcodes, and then rebuild the strings, and then reset the register and do it again. You can see some of the opcodes in the bottom left. I know it's a little hard, but I didn't want to implement the entire like state machine because we didn't need to. We only needed to implement the ones where we parse out the symbols and keep them going. But yeah, so it's pretty fun, but it's definitely just a flex on like the original like Mach-O specification because you have prefix trees and finite state machines. That's cool. But going into the actual wins and stop nerding out about data structures. Back at the start of the year, Patrick blogged about DPRK's spectral blur. I think Greg also with 100 Days of Yara talked about it around the same time. We actually get into looking at the exports, and you see that there's some exports that we can parse out. And there wasn't another like solid way to kind of track this, like looking at dilibs or entitlements. So we actually went ahead and parsed all of the exports and provided some helper functions. We do have export hashes, but we also have helpers like has export. So if you want to check if a binary gives a specific export, you can do that with the module as well. And one thing to note here is previously with SimHash, if you're using it on a Mach-O binary, if the symbol table was stripped out of the binary, you were just kind of left in the dark. You didn't really get to see anything. Because I went through and parsed out everything with the prefix trees and the finite state machines, we get those even if the binary is stripped, because they have to be in there. And then with import hashing wins, it was also useful for clustering samples from Windows Server that Kaspersky blogged, I don't know, earlier? 2023, yeah, towards the end of the year. And we were able to actually go ahead. We also parse out the R paths. We don't really go into that one too much in depth, but it's just a run path. So like when it links, it looks for that specifically when the linker goes through everything. So we were able to do import hash or look for the specific R paths in the binary. But it's important to note that like this is not a silver bullet. This is not a panacea. There are things where it's going to fall short, and we would be amiss if we did not mention some of those things that we ran into when we went through this process.
Yeah, and unfortunately that happened with probably the coolest backdoors that we're going to talk about, but we got to keep it real. So the two backdoors we're going to talk about, we assess, and I think a bunch of others in our space do too, that they came out of sort of the Mata or Dackle's original sort of code base. One became what on the Windows side is called Matador or Mata v4, and in the macOS space is called tie-dye. And then Mata v5 on the Windows side called Stratosphere by Mandiant on the macOS side. So we think that this sort of code base is Trader's kind of crown jewel because of its extendable architecture and all it can do to really facilitate a compromise. Unlike a lot of families we've covered, Mata v4 or tie-dye can persist based on privileges, either as a launch daemon or a launch item, which obviously isn't insane to anybody in here, but because it's relatively rare in the sort of macOS malware space, it felt important to highlight it. But sort of the cooler stuff it can do is it loads all of these plugins to facilitate additional things that it can do. And of course, it can do all the typical stuff like loading a reverse shell, upload, download files. It can scan the host for particular file paths or types of interest through its own sort of native code. In my opinion, the coolest and kind of scariest things that it can do is it can create a reverse peer-to-peer connection to sort of chain infections across an enterprise. So if my macOS box is air-gapped but connected to the rest of the network, they can pop Jacob's box and effectively use it as a tunnel outbound. And we used to, sort of in the threat intel space, glorify a Russian group called Turla for their snake and sort of carbon families that could do exactly that. And Trader now has that both on the Windows side and the macOS space. So I wanted to give them their due. One of the challenges has been, though, with both that family and then this family we're going to talk about is sort of just lack of public samples. The probably most impressive family that they have is a family called Stratosphere, and again, it's a modular backdoor with sort of this reverse, all these sort of embedded encrypted protocols, and it can support for C2 traffic that can also be proxied, used in server mode, not just in client mode. Kaspersky, to their credit, wrote a really good paper on the Windows variant of this and all of its sort of really impressive buffer box and internal communications that it uses. So I'd really recommend reading that because they do a way better job explaining it than I ever could. And there is fortunately a public sample of Stratosphere on VT that no one seems to really be aware of. I will share the hash in the OBTS Discord. The challenge is that it's a dump. So if anybody can sort of figure out how to get it to be disassembled, kudos to you, but all of the strings are in there and it matches the Mandiant rule that they put out as part of the Jump Cloud blog. But because this is objective by the C, a friend of the program has shared a packed version of the Stratosphere backdoor that I cannot crack. And so if anybody wants to hang out after lunch or during lunch and sort of party wave reverse this and try and crack it, we know that it's Stratosphere based on the C2 comms. We should do that. I think it'd be kind of fun. You're going to have to come talk to me in person, though, because I'm inherently an untrusting individual being in the Intel space. So yeah, get ready to smile and try and woo me to get the hands on this sample. But yeah, with that, sort of wrapping up this presentation and looking ahead, the best and worst thing that happened this week was YARA-X got put into VT as the engine both running retro and live hunts. So Jacob's code is now in VirusTotal. Let's give him a round of applause for going from a 9x engineer to a 10x engineer. Congrats on your promotion. So this was great for Jacob and awful for me because I had 18 months of assumptions based on local files that I then had to face the burden of retro hunting and deciding, am I going to have all my assumptions proved wrong because I now have scale to test this against? Thankfully, because you see me still up here presenting, we had validation. So two of the main rules that we showed you, the sort of apple juice, dilib, and entitlement hashing, and the TA444 Bluneroff candy corn sample, we ran that over the last year VT, and it did all the hashing, all those Mach-O files. Only 19 hits. So I would call that a win. I haven't triaged all of them fully. But given the rarity of that, I'm just going to have those as a live hunt going forward and hope that more malware comes in and matches that to make me feel good about myself. So because I was a little bit mean earlier about the L word, I wanted to leave some of you with a pocket guide of the DPRK ABCTTs of sort of a decision tree of how to figure out what you're looking at. So if you see any of the stuff, especially that Chris talked about in his presentation yesterday in Swift, it's probably Bluneroff. If it talks to hostwinds, again, probably Bluneroff. We didn't touch on contagious interview because, but there's sort of this weird outlier that is tied into the IT workers more closely. Again, a whole bag of worms to get into, but a pretty easy way to pivot on them. It's Jade, Sleater, Trader if it's cool. And if it's anything else, it's probably apple juice. So,
Cool. So the main takeaways that we really want to highlight, all of the code and the modules that we've shown, it's now live in VT, and you can also grab it from GitHub. You can use it in your Python scripts, just pip install YARA-X. It's available pretty much everywhere, and it's going into like v1.0 very soon. We do want to remind you that lightweight feature-based similarity does not equal code overlap. Greg and I are not super cracked reverse engineers like some of you in the room. So we're not making that claim, but it does help us be able to see that binaries are similar. And we especially want to highlight that the signatures on the metadata, the dev preferences, regardless of project, allows us to track not just very similar malware families that are being clustered, but also things that groups are working on that may not be exactly the same thing or in the same cluster, but using the same things on the back end. And one thing I want to mention is that this is still ongoing. We're still parsing out and implementing newer features. I just had one merged earlier this week for embedded linker options in Mach-Os. So if you spend any amount of time with like actually compiling and writing Swift or Objective-C or anything like that, you can embed linker options. We're going to start pulling those out so we can see kind of how you compile the binary and use that as well to see how developers do those things. If you find any bugs, please tell me. Like, report it on GitHub, ping me. We're going to give our socials after this, so you can message me at any time you want. Please don't, though. And then just use it, break it, do all the cool things. If something doesn't look right, just yell about it, and someone in the community will help.
I think before, obviously, we're not taking questions, but there are a lot of people within the YARA project, like Victor, Tomas, and Wes. They've been really helpful for us, and then everybody sort of behind the scenes in the macOS and North Korea tracking space that have also been willing to share samples or insights. So we have a lot of people to thank. It's not just us, but we're going to be up here to take the credit. So thank you for your time.